In this video, we're going to take a look at linear inequalities in one variable. So first, what is a linear inequality? Well, a linear inequality in x can be written in any one of the following forms where a, of course, cannot be 0. That is, ax plus b can be less than 0, ax plus b can be less than or equal to 0. Ax plus b is greater than 0, or ax plus b is greater than or equal to 0. Technically, I could also call the linear inequality ax plus b does not equal 0, but that's going to be exceptionally rare and not really covered in this course. Now, in general, when we multiply or divide both sides of an inequality by a negative number, the direction of the inequality symbol is reversed. That's the key to getting these correct. They are solved just like linear equations, with the exception that I have to actually pay attention to flipping my sign when I multiply or divide by a negative. So our first example of linear inequalities is 2 minus 3x is less than 5. Now, I'm going to solve this very much the same way as I solved the linear equation. Since they said plus 2, I'm going to say minus 2. And 5 minus 2 is 3. But here's where I come across my first little issue, and that is I need to divide by a negative. I can't just draw my line under it and put negative 3 because then I'll forget to flip my sign. So I do typically, actually this is why I quit writing the steps out, because I got tired of writing it every time. But as I divide by negative 3, I've got to flip that sign. Okay, so that leaves me with x is greater than or equal to negative 1. And so my solution set in interval notation says start at negative 1 and you can keep going forever. There's my solution set. Now, I want to point this out because I want you to see a way to check. If I substitute negative 1, then I end up getting 5 equals 5, and I have not checked to make sure I've got the inequality right. But if you look at where that falls on a number line, I have started down here at negative 1 and colored everything in this direction. Okay, by the way, I was supposed to graph it anyway. And here's the 0. If I plug in 0 and it works, I know I went the right way. If I plug in negative 1 and get equals, I got the right end point. But if I plug in a number that got colored in, it's part of my solution, and it works, I know that I went the right direction. So if I want to check the 0, 2 minus 0, and 3 times 0 is 0, 2 minus 0 is 2, is less than or equal to 5, that is true, so I know that I did in fact end up changing the sign when I was supposed to. So I know you're wondering, can they give me those fractions like they did with equations? Yes, they can, and I still work them the same way. I look at what I have here, and I look at my denominators, and I say I've got a common denominator of 12. So I say x plus 3 over 4. Now I'm multiplying by a positive 12, so I'm not flipping my sign, times 12. Greater than or equal to 12 times x minus 2 over 3 plus 12 times 1/4. Again, I am multiplying both sides, but at the same time I'm distributing on the right-hand side. Now 4 goes into 4 one time and into 12 3 times. 3 goes into 3 one time and into 12 4 times. 4 goes into 4 one time and into 12 3 times. Do notice that all my denominators are now 1s, so I don't have to express them. And what I'm left with is 3 onto x plus 3 is greater than or equal to 4 on to x minus 2 plus 3 times 1, which is 3. Now I'm going to use the distributive property to get rid of all parentheses. And 4 times x is 4x, 4 times 2 is 8. On the right-hand side, I need to collect like terms. So I've got 3x plus 9 is greater than or equal to 4x. Negative 8 and 3 is minus 5. Now, it does not matter which direction you go in, but I have a good many students who finally learn to go to the right because it keeps them positive and then they don't have to flip the sign. So I'm going to move my x's to the right by saying minus 3x on both sides. And 4x minus 3x is 1x. And then, since they said minus 5, I'm going to say plus 5. And I get that 14 is greater than or equal to x. Now, if you want to turn that around so that x is on the left, be sure that since the arrow was pointing to the x, that you keep the arrow pointing to the x. That means x is less than or equal to 14. Okay, so on the number line, I'm going to count by, I don't know, let's say 7s, so I'm not taking up so much time. I would count by 7s, and or equal to is closed, so it'd be a bracket, and everything this way gets colored in. Okay, and the interval notation looks just like it. See, negative infinity, that got colored in right here in the arrow, up to 14, and it is closed. Again, this is why we like the interval notation. It actually looks like our number lines if we use the same symbols. Okay, let's do another one. Okay, I warned you that this is a special case by putting it up here in the title, so you might want to pay careful attention as to what happens, because this is something that does happen occasionally. 2 times x is 2x, 2 times 4 is 8, so I still distribute to get rid of parentheses. And I'm going to move all my x's to the left, so I'm going to say minus 2x on both sides. And when I do, I get that 8 is greater than 3. Well, this is a numerical statement that happens to be true. This falls along the lines of the equations we looked at and said that there was such a thing as an identity. And when it comes down like this, it's true for all real numbers. Well, we don't write out words for all real numbers anymore. We just say include everybody on the number line. And this is how we say it. And if I have to draw it for you, I draw the number line, I show you my 0, I pick out a few more points, and then I color in the entire number line. All real numbers. If my x's go away and I'm left only with numbers, if the answer is a true statement, then my solution set is all real numbers. For our last example, we're going to look at another special case. If I subtract x from both sides, I'm left with 7 is less than or equal to negative 2. A positive number has never been less than or equal to a negative number. So this is a false statement. And where the true statement gave me the solution set of all real numbers, the false statement gives me an empty set. If I have to draw it on a number line, all you see is a number line with absolutely nothing colored in, because you will never find a number that will make 7 less than negative 2. So as I'm dealing with inequalities, I may come up with a couple of special cases occasionally. It's no big deal. Just remember that it's okay to say sometimes all real numbers will work and sometimes none will.